We're going to be looking at the stereochemistry of carbohydrates. So all of our carbohydrates are either going to fall under the D or L configuration. Since oftentimes carbohydrates are going to have multiple stereocenters, that D or L is going to be based on the highest numbered asymmetrical carbon, which is often going to be the one that is furthest from the carbonyl carbon. So whenever we're looking at these, realize that yes, we are going to have multiple stereocenters, but that's going to be based on the one that is furthest away from the carbonyl carbon. Therefore, when we're looking at whether it's D or L, we're going to be looking to see if the hydroxyl group is going to be on the right side or the left side in this flat projection. So it's going to be D if it's the hydroxyl group is drawn on the right. And what you're going to find is that the most naturally occurring carbohydrates are going to be D isomers, which I mentioned in that intro video. We're going to have three different words we're going to use when we're dealing with linear carbohydrates. So yes, we are going to also cyclize them, and then we're going to add another one when we do that. But to start off with, in our Fisher projections, we're going to have three different terms. We're going to have enantiomers when they are mirror images. We're going to have diastomers when they're not exactly mirror images, but there's definitely things that are different, that are opposite configurations at one or more chiral centers. Lastly, we're going to have epimers when they're different at only one chiral center. And what you may notice is that epimers are a specific kind of diastomer. So diastomers are different at one or more chiral centers. Epimers are more specific in that they're different at only one chiral center. So this is an example of enantiomers, where what you have is they are mirror images. So looking at all the different chiral carbons, what you see here is that you've got this lovely set where everything is exactly opposite. So everything that was on the left in one side is on the right in the other. So they're not just different at one place, they're different at all of them. And that's what's going to give us those mirror images. What we have here are diastomers. So you can basically look at a lot of these couples as being diastomers. When we're actually looking at these, what you'll notice, first of all, is that highest chiral carbon, which here is carbon 5, you're going to see that hydroxyl group is drawn on the right. So that's where all of these are D. Then from there, you'll notice that you've got a lot of different things happening. So we could look at all kinds of different pairs of these as being diastomers. And we could even look at some of these as being epimers, where they're only different at one chiral carbon. So if we take a closer look at, say, D-allose and D-altrose, those are actually epimers. They're actually only different where that highlighted carbon is yellow. But remember, that also means that they're diastomers. So D-allose and D-altrose are both diastomers and epimers. But you can kind of play the game and look through all of these and kind of see like which category do they fall into, and can you spot where our epimers are, which ones count as diastomers. It's pretty much all of these count as diastomers along this set. So now that we've looked at the things that are linear, now we're going to go ahead and cyclize things. You probably noticed that there's lots of alcohol groups on there. So when you take one of those alcohol groups and that oxygen basically does an attack on the carbonyl carbon of that aldehyde, or could be our ketone, we're going to get so if it's an aldehyde, you get a hemiacetal. If it was the carbonyl carbon on the ketone, then we would get a hemiketal. So here things are drawn, the reaction here is drawn with the hemiacetal. What this is going to also do for us is this is going to give us an additional asymmetrical center. So where that either aldehyde or ketone is now going to create an additional asymmetrical center. With these, you may have noticed that there's a lot of alcohol groups in these carbohydrates. And the 5 or 6 membered rings are going to be the most common. So those are going to be the ones that we stick with. So even when you're looking back and you're like, oh, I see lots of alcohol groups, this could go lots of different ways. For stability, we really are going to just focus on the 5 and 6 membered ring and not get creative and be like, ooh, but what about the 4 membered ring? If you think back to your organic chemistry days, remember those are 5 and 6 are the more stable configurations, usually due to steric issues. So we're going to then talk about what these two different kinds are. So a 6-membered ring is going to be a Pyranose, and a 5-membered ring is going to be a Furanose. And here it is again. So notice that when we're looking at these, you are going to have oxygen as part of the ring. So when we say 5-membered ring or 6-membered ring, we do still have the same number of carbons that we had before. So you will still have the 6 carbons. So we're starting with glucose, which has 6 carbons. We still have all 6 carbons, but one of those carbons or 2 of those carbons are actually above the ring. It just depends on if we're in our 6-membered ring, our Pyranose form, or if we're in our Furanose form. So those are both terms that you guys should be familiar with as we go along. Since we now have an additional asymmetrical center, we are going to then have to add how we're going to describe these. So if we are cyclizing glucose, and we were talking about our Enantiomers, we're going to stick with our D-glucose. When we cyclize this together, we're now going to have 2 different options, alpha and beta. As one of my favorite trick for this is, as long as we started with D-glucose, in the alpha version then of the Hawthorne projection, so notice that when we have this cyclized ring, this is now a Hawthorne projection. When you have the Hawthorne projection, if you started with D, the hydroxyl group for alpha will be on the bottom. The beta will be on the top. Now, there's another way to do this, which we can do in the Fisher projection, which basically talks about if they're on the same side or if they're on opposite sides. So now what we need to do is if we're looking at the Fisher projection, which looks linear, but notice now that we have this oxygen, it's not linear anymore. If the oxygen is on the same side as our hydroxyl group, then it's going to be the alpha form. If it's on opposite sides, it's going to be beta. So again, when we go through, here we are looking at D-fructose instead. Fructose usually creates a furanose, so we usually have a 5-membered ring when we're looking at fructose. So essentially this is the same general notion, but this just has showing you then with a 5-membered ring instead of a 6-membered ring. And then the difference between those alpha and beta are called anomers. Here are those tips. So this is also going to include the tip for a Fisher. So when the hydroxyl group with the anomeric carbons on the same side, as the oxygen is the highest numbered asymmetrical carbon, that's how you know that it's alpha. But again, I prefer the simpler rule that we covered. The other thing with conformation of sugars is realize that in real life, things are not nice and flat rings in this case. You guys probably noticed that we do not have conjugated double bonds. So these are going to be sp3 carbons, which means that you're going to have that 3-dimensional shape. So you're not going to have a flat ring like you do in benzene when you have those great sp2 hybridizations. So because of that, usually would have some sort of 3-dimensional shape, usually either a chair or a boat conformation. The boat conformation is not typically favored. Usually we have the chair conformation. Your chair conformation is still going to come, has an equilibrium between which ones go up, which ones go down. And as you look here at the at the axial versus equatorial, what you'll notice is that equatorial should be in the plane. So whenever we talk about something, so yes, I know that we have a chair conformation where we have something that goes up, something that's in flat, and something that goes back down again. But even with that, realize that anything that's equatorial should then be in the plane of the carbons. And anything that is axial then is going to stick up out of things. So our axials are either going to be sticking up or sticking down, and our equatorials are going to be nice and in the plane. We can also have sugar derivatives. So whenever we're talking about carbohydrates, we can still have different functional groups in here. So as you look at these different derivatives, sugar acids, sugar alcohols, deoxysugars, sugar esters, amino sugars, and phosphosugars, all of those should remind you of different things from organic chemistry. And they're going to go really well along with what we've got. So before we were looking at different carbohydrates, and we talked about something like glyceraldehyde, and now we have glycerol. Or looking at any of these, we basically have lost that carbonyl carbon. So when we're looking at all of our sugar alcohols, there's no more carbonyls, everything's just alcohol. Below, since we do usually have some sort of oxygen attached to all of our carbons, we can also have deoxysugars. So where we originally would have had ribose, we can actually remove one of the oxygens from that. So here you have 2-deoxy alpha D ribose. So D naming that's stereoisomer, alpha, because you can see that hydroxyl group is in that down position, deoxy then on that 2, because you can see that you remove that second oxygen. And you can go through the rest of the examples to kind of get a handle on what these look like. We've got a couple more sugar derivatives. As you might imagine, if it's a phosphosugar, we're adding a phosphate. So just keep in mind, again, we're in biochemistry, so whenever we're talking about phosphorus, it's never phosphorus by itself. So phospho is going to be a phosphate group. Similarly, when we talk about amino sugars, this is going to be adding an amine. Now, what I do want you to notice is oftentimes when we're naming these, oftentimes we're going to be naming these off of the original root carbohydrate. So when we have things like glucose 1-phosphate, you basically do get to keep all of that wonderful terminology of the glucose and then just add where the phosphate's going. Or if we're talking about glucosamine, again, you have kind of that root of glucose and then adding that amine to it. Some of them are then more specific, so there are also things like sugar acids, and oftentimes these will have their own different unique names, where now we have muramic acid. Granted, we're also adding some carbons to this, so you do have a fairly distinct and different structure. And as you might have guessed, since we now have acids as a different functional group, that is a carboxylic acid.